Imagine two ancient stars locked in an endless cosmic dance, slowly spiraling toward each other across the darkness of space. Invisible to the naked eye, silent for now. Yet one day their fatal embrace will unleash an explosion so bright it could outshine entire galaxies. But don't panic just yet. Today we journey to a stellar system surprisingly close to home and learn why this discovery reshapes how we understand the universe itself. In the endless ocean of stars, some hide in plain sight. Roughly 150 light-years from Earth, astronomers have identified a pair of white dwarfs, the dense remnants of dead stars, bound in a gravitational ballet that will eventually end in a cosmic firestorm. This is not science fiction, it is a scientific inevitability, though one scheduled billions of years into the future. Their eventual collision will trigger a type Ia supernova, one of the most energetic events in the cosmos. But why is this important? The answer takes us into the very heart of modern cosmology. Type Ia supernovae are no ordinary stellar explosions. They are some of the brightest beacons we can observe, visible from billions of light-years away. Their significance, however, goes beyond spectacle. These explosions serve as what scientists call standard candles, cosmic mile markers that allow us to measure vast distances across the universe with surprising precision. The idea hinges on a simple but powerful assumption. Every type Ia supernova shines with nearly the same intrinsic brightness. How can that be? The answer lies in a remarkable astrophysical principle known as the Chandrasekhar limit. White dwarfs made of degenerate matter can only support themselves against gravitational collapse if their mass stays below about 1.44 times the mass of our Sun. Cross that threshold, and a white dwarf becomes unstable, leading to runaway nuclear fusion and an explosive death. For decades, astronomers believed that every type Ia supernova resulted from a white dwarf accumulating enough material from a companion star to cross that limit and explode, yielding a predictable luminosity every time. However, nature rarely stays neatly inside human boxes. Over the past 2 decades, astronomers noticed something unsettling. Not all type Ia supernovae look the same. Some burned a little brighter, others curiously dimmer. This inconsistency challenged the foundational assumption behind using type Ia events as standard candles. If their brightness varies, could our cosmic measurements, including estimates of the universe's expansion rate, be wrong? Real-world example. In 2011, astronomers studying distant supernovae discovered variations that could not be easily explained. It was as if some explosions were overweight, leading scientists to question whether collisions between white dwarfs might also produce supernovae instead of mass accumulation alone. New research, including the discovery of this nearby binary white dwarf system, provides strong support for the white dwarf merger model. Here's the process in simple terms. 2 white dwarfs orbit each other closely. Over time, they emit gravitational waves, ripples in space-time that rob them of orbital energy. Gradually, their orbit decays. Eventually, they merge. If the resulting mass exceeds the Chandrasekhar limit, boom, a supernova. The fact that the new system is just 150 light-years away is astonishing. It implies that these ticking time bombs are scattered throughout the Milky Way, perhaps in greater numbers than we imagined. Yet in the grand scheme of things, their timelines are leisurely. The newly discovered pair won't merge for another 23 billion years, long after our Sun has burned out and Earth itself has ceased to exist. The white dwarfs in question orbit each other once every 14 hours, an incredibly tight embrace by cosmic standards. Over the eons, gravitational radiation will shrink their orbit until they eventually collide. When they do, they are expected to form a merged object of roughly 1.56 solar masses, slightly above the Chandrasekhar limit. Interestingly, not all mergers produce identical explosions. The final brightness depends on the total mass and composition of the merged object. A collision yielding 1.56 solar masses may look very different from one involving 2.0 solar masses. This helps explain the slight inconsistencies observed in real-world supernovae. Case Study 1. In 2003, astronomers observed a supernova that defied expectations. It was brighter than any Type Ia supernova previously recorded. Later analysis suggested it originated from a merged white dwarf system with a combined mass exceeding 2 solar masses. Case Study 2. The famous standard candle assumption helped reveal dark energy in 1998 when 2 independent teams noticed distant supernovae appeared dimmer than expected, implying the universe's expansion was accelerating. Without standard candles, that discovery would have been impossible. But what if our candles weren't so standard after all? If Type Ia supernovae vary more than previously thought, some measurements of the cosmos could be off. Distances to remote galaxies might be slightly miscalculated. The inferred rate of cosmic expansion, known as the Hubble constant, could need fine-tuning. This isn't cause for panic, but a reminder. Science evolves. As our tools sharpen and our observations deepen, so must our models. The discovery of this white dwarf binary forces cosmologists to think more critically about the assumptions baked into their calculations. In a way, this new understanding mirrors much of human progress. We build models, we test them, we find exceptions, we refine. Astrophysics is not just about mapping distant stars. It's about humbly recognizing that the universe often defies our neatest theories. Just as early map makers redrew continents when explorers brought back new reports, scientists today are redrawing the cosmic map, one white dwarf at a time. So what can we learn from 2 tiny dead stars pirouetting in the dark? That the universe is more complex and more wondrous than we imagine. That even the most standard rules have exceptions, and that cosmic violence on unimaginable scales can offer insights that light our path to understanding. In the grand timescale of the cosmos, we are momentary flickers, but thanks to discoveries like this, our flicker illuminates the infinite. Stay curious, stay humble, and never stop looking up.